Okay, yeah, so thanks a lot for the invitation. Great to be here. So this is my first time. And the talk today would be, so we've been talking about random matrices for the whole week. And the goal here would be to sort of use some of that information to sort of answer some geometric questions in percolation models. So that's sort of the broad goal. And sort of at some point, we'll sort of use connections to random matrices and use sort of precise rigidity properties for eigenvalues. Okay, so many of you might not be familiar with KPZ, although you will hear some of that in Sharav's talk later. But let's sort of go through sort of 1 plus 1. So even though the later talk would be about 2 plus 1 dimensional setting. So this is 1 plus 1 dimensional model since in Z2. So you have Z2, so yep. And for every vertex, you have a random variable. So this picture is in the dual lattice, so here the faces are vertices, but you can think of either. And so they're all IID. And given such a noise space, you look at oriented paths between points, all right? So let's say this is the origin, and this is, let's say, n comma n if the box has size n. And then you look at some oriented path which goes from 0 to n, and that path now will have a random length, which is the sum of the variables along that path, right? So for any path pi, you look at summation of xij along pi. And the object of interest would be what is known as a geodesic or a polymer, which is the path that maximizes this weight, all right? So Tn would be the maximum over all paths pi, which are oriented, the sum of these weights. And so as I said, so this Tn would be the object that we would care about. And more importantly, we would sort of also care about the random path gamma n, which attains this maximum, right? So that's the setting. And yeah, so like I said, so we would try to understand asymptotic properties of Tn, and more importantly, geometric properties of this random path. So any questions about the model? Okay. And so I'm like, there are a bunch of connections to this. So this is a percolation model, but it turns out that there are a lot of connections with other particle systems. So the most well-known is what is known as a totally asymmetric exclusion process, or TASEP. So where you have a bunch of particles on the line, every site has at most one particle, and particles at rate 1 independently try to jump to the right only if the jump is allowed, in the sense that the site next to it is empty. It turns out that this has a direct correspondence with the previous percolation model when the entries are IID exponentials. So here, the way I've defined it, xij's could be any IID variable as long as they're positive. And so yeah, so TSF would be corresponding to the model where things are exponential, and roughly the correspondence is this. So if you start from all particles to the left of the origin, every side to the left of the origin is full, and everything to the right of the origin is empty, then the time it takes for the nth particle to cross the origin would exactly be in distribution similar to the last passage time between 0, 0 and nn. Okay? So the weight of the random path in the percolation model is exactly the time it takes for the nth particle to cross the origin in this particle system. So there is also some growth process known as the corner growth process that also encodes the same information. And there are other particles which have similar flavor and are corresponding to some other sort of similar percolation models. One of them would be what is known as the Hammersley process. Here it's a continuum model. Things are on the real line, and particles jump uniformly to the right between the next particles. Okay, so the precise definition is not important. The main point is that there are many particle systems which have this correspondence with percolation models. This one in particular is connected to what is known as a Poissonian version of the last passage percolation. I'll sort of shortly describe it. And so roughly what it is the longest path. So here the discrete model had a bunch of random variables. So I took the longest path. Here it's a bunch of Poisson points, and you want to look at the path which is oriented and passes through the maximum number of points. And again, there is a growth model which is associated to this, which is known as the PNG, or the polynuclear growth model. And so, okay, so this is sort of a pictorial description of the Poisson last passage model. So you have a square box of size n, let's say, and you throw a Poisson process of intensity 1 inside that. Okay, so the points are scattered, and now you want to sort of join, let's say, the left bottom corner to the right top corner. So this is 0, and that's n. And you want to look at an oriented path which passes through the maximum number of points using this Poisson process. And a sort of quick thought actually reveals that this is also sort of quite closely related to what is known as the longest increasing subsequence problem for a random permutation. Okay, so how does that come about? So suppose we fix the total number of points that land in the box. Okay, so that's a Poisson variable. So let's fix that. Then the distribution of the points are uniform, right? If I just fix the number of points in a Poisson process, then the distribution of the points would be uniform. And now you can order the points according to their x coordinate. So, okay, I'm not clear which one has a smaller x coordinate, but you can order them. And given that ordering, the y coordinates form a uniform permutation, right? And so you can sort of convince yourself that this path that is the longest oriented path passing through the most number of points is also exactly the length of that path is also exactly the length of the maximal increasing subsequence for this associated permutation. The Wedge initial condition for the particle system would be this. So this is the negative axis. Every side here is initially full. Every side here is initially empty. And now you want to understand when does the nth particle here sort of cross the origin. So again, back to the general setting where we did not assume anything about the edge variables or the vertex variables. So under suitable moment conditions on the distribution of those variables, a subadditive ergodic theorem would imply that there is a shape theorem. So remember, Tn in our notation was exactly the passage length between the origin and n. So a subadditive theorem would tell you that Tn over n converges to a constant, and that constant, of course, will depend on the distribution of the individual variables. In particular, you can also have a stronger theorem where you actually try to sort of look at passage times between various points. So, right, so this was your box. This was the origin. Initially, what I said was I was only looking at paths which ended up at n, but now you can look at different paths ending up at different points. And so you can look at the distance function as a function of xy. And there is and a similar sort of application of the ergodic theorem would tell you that the whole thing as a process in xy will converge to a shape theorem. And again, natural superadditive properties of the definition tells you that the boundary of the limit shape, so Tnx ny would exactly be the distance between 0 and the point nx comma ny. This says that there is a limit, and you can look at the boundary of this limit shape, namely the set of all xy says that this is exactly 1, and just using superadditive properties of the distance function, right? So it's a superadditive random variable. So if you go from 1 point to nn and also to 2n, comma 2n. So if you look at the path which goes through n, so these two paths have the same distribution. So, but the best path from 0 to 2n could be something else. So this tells that this distance is at least this distance plus this distance. So this is the natural superadditive property of the definition. And so it tells us that the limit shape is actually convex. Okay? Now you can talk about fluctuations. So under mild conditions, Poincare inequality would imply that the variance of Tn would be order n. So fluctuation being at most root n. Okay. Okay, so there are two things that we will sort of go back and forth between. So one is the quantity Tn itself, which is a real number, which is the length of the path, and the other would be the geometric object, which is the path itself. And so if I understand, so the whole hope would be to translate information about one to the information about other. So if you understand something about fluctuation of Tn, you can try to say what does it imply about the location of the path, right? And under this convexity assumption of this shape of this limiting shape, this directly implies that the fluctuation is already little of n. So what does that mean? Right. So this is my diagonal, and I have some random path which reaches the maximum value. And what this says is that just saying that the variance is order n would imply that the fluctuation of this random path from the straight line would be little of n. So there is already some localization. Okay, so this fluctuation, the deviation is already smaller than the system size. So any questions? Okay. But now we can try to sort of make more refined predictions, and this was done by this famous paper by Kardar, Parisi, and Zhang in '86, which predicted that under pretty mild conditions, these exponents governing the fluctuations are universal, and they're governed by the so-called KPZ equation, which we'll hear more about in the later talk, but in a different setting. And so the predictions are roughly this. So again, there are two quantities, Tn and gamma n. Tn is the real number, which is the length of the path, and gamma n is the path itself. So the prediction is the variance of Tn is like n to the 2/3. So the fluctuation should be n to the 1/3. So that's the longitudinal fluctuation exponent. And I can try to say, and I can try to see what does it say about the path itself, and this is what we'll be calling as transversal fluctuation. And the prediction is that the exponent should be 2/3. Right? So the description here, which says that the fluctuation is little of n, is predicted to be like n to the 2/3. Okay? And so the real reason, so I'll sort of describe the heuristic governing this. And the real reason is, if you look at the distance function as a function in xy, it has a globally like a parabolic type of behavior, so it sort of decays quadratically, but then the local fluctuation is given by Brownian fluctuation. And so if you try to sort of see how these two things interact, you can sort of arrive at these two exponents. Okay, so I'll do that shortly. And then you can talk about scaling limits. So these are the exponents governing the fluctuation, but now you can try to see, oh, you centered the mean, divide by the standard deviation, and the scaling limit should be, so now it's, you should expect it to sort of converge to a random variable, and the prediction is that for many general models, the limiting distribution should be given by a Tracy-Widom type object. Okay? And there are several other predictions as well. We will not go into that. So our primary interest would be these two things. Okay, so this is basically what I described here. So what is precisely the transversal fluctuation? So here is an oriented path which goes from 0 to n. And this is the straight line, the diagonal. And so of course, because of the oriented nature of the path, it will intersect every anti-diagonal line exactly once, just because of the definition. Now I can try to see for any line, so these anti-diagonal lines are given by the equations x plus y equal to t for some t, right? Let's look at one such line. And now I can try to see, okay, so let's say xt comma yt is the point through which the polymer passes, which lies on this line. And I can try to measure how much further away from the diagonal it is. So dnt would be exactly the transversal fluctuation of this path on this anti-diagonal line x plus y equal to t, all right? And so we would be interested in dnt as well as the supremum of dnt over all t, like what is the maximum possible fluctuation that the path can reach. Okay, so we said that the prediction is n to the 2/3 for this quantity. The transversal fluctuation should be like n to the 2/3. And I said that the real reason is something called globally parabolic versus locally Brownian. So what does that really mean? It's okay, so the picture, I'm not sure how helpful it is, but okay, so if you want to figure out where the path passes through, so let's say this is the main anti-diagonal, and for the moment, let's just restrict ourselves to where the path intersects this line, okay? So the transversal fluctuation is a global thing, but you can just look at the local transversal fluctuation on this anti-diagonal. And let's say, try to come up with a heuristic which says that this thing already should be like n to the 2/3. Okay, so here is a point, origin. Here is another point, n comma n. And you want to find the best path from this point to this point, right? Now, what is one way to do that? So forget this point. Let's try to measure the distance from the origin to this line, okay? So that's a process on this line. So you can try to draw the graph of that. And that graph, I claim, I'm like, so that should be roughly maximized at the midpoint, and then should have a sort of a parabolic behavior. So if this distance is n, this parabola roughly has an equation which is like minus x squared by n. in some different coordinate. Let's say this is the maximum so think of this as now the new origin, and now this is a parabola about that, but the decay is like minus x squared by n. And now you have some fluctuation on top of that. This is sort of the hydrodynamic limit. So the actual path will be some sort of actual distance profile will be some sort of a roughened version of that. And so that's really what that picture shows. So now you can try to do some computation, right? So the parabola is given by minus x squared by n, and you put a Brownian motion on top of that. So that has fluctuation which is given by square root of x, okay? And I can try to find the x for which this thing is maximized. I can do some computation, and it's not hard to check that this is sort of the x for which this is sort of roughly maximized is going to be of the order of n to the 2/3. Okay, so we did not care about the n for the moment, so we just looked at the distance profile from the origin to the straight line and saw that the maximum distance would be like n to the 2/3. Yeah. So it will be clear when we sort of go to the actual model of Poissonian or exponential. So I'll sort of talk about it then. No, so the point is, yeah. So I'll talk about that when we go to concrete models. And the point is, like, if you look at this distance profile, but so the eventual goal is to reach here. So you can do the same thing from here. So you have another Brownian motion here. And the sum of these two parabolas would be a parabola itself, and then the sum of two Brownian motions would also be a Brownian motion. So the same intuition would work. And that will tell you that the best path from origin to end would sort of roughly pass through some place where the distance is like n to the 2/3. Okay, so that's really the reason why the fluctuation in space is given by this exponent 2/3, but that also gives you the fluctuation in the value of the polymer, because the fluctuation in the value of the polymer would be just like root x at x equal to n to the 2/3, which is now n to the 1/3. Okay, so this is really the geometric reason why you would expect this 2/3, 1/3 exponent showing up. Any questions so far? Yeah. Yeah, because so you're passing through an IID noise, and so you will have local fluctuations which are going to be given by sums of IID things and things like that. At the point 0. No, so this whole thing is sort of transition invariant, right? So you don't care about, so you can pin everything to 0, right? So you can think of the Brownian motion as having like value 0 at 0, because the whole thing can be translated, and that does not really affect this argument. Okay. Okay, so this is sort of the general heuristic, but the point is when can one make this rigorous? And so this is where sort of people have been studying integrable models, where you have some other connection that you can exploit to try and prove these things. And so all these predictions are only known rigorously for some handful of models, and these are what are known as integrable models. So one example would be last passage model with exponential weights, which are connected to this particle system which I described, or even geometric weights, where the variables are IID geometric random variables. The Poissonian model is also understood well, and you can also verify the predictions here in this context, and an associated problem of increasing subsequence in a random permutation. Another model where things turn out to be tractable is what is known as the O'Connell-Ayyer polymer, which is connected to a last passage model where the noise is given by Brownian motions themselves, and this is connected to what is known as Dyson-Brownian motion. And okay, so far I've been talking about zero temperature models where I was looking at the path which has the maximum length, but you can also talk about positive temperature models where you put some Gibbs measure on paths where the Hamiltonian is e power beta times the length. And so there are some models where people also understand things, and these are some examples: the log gamma polymer or the continuum directed random polymer, which is connected to the solution to the stochastic heat equation. And like I said, so in most of these things, the analysis is sort of based on some bijections or exact formula or connections to some algebraic objects. So either you have some connections to random matrices, or you can connect them to things like Young diagrams in algebraic geometrics and other things. Okay. And so if you have such a tool, then you can try to analyze them and try to sort of reach the conclusion that you geometrically expect to be true in more general contexts. Okay, so what is known? So like I said, so the Poissonian LPP case is known, and there the there the correspondence that people use are connections to permutations and Young diagrams. So this is what is known as the RSK correspondence to Young tableau, and it turns out that the shape theorem is given by this function which is square root xy. And again, this is the fluctuation result where you center by the right thing and divide by n to the 1/3, which you expect to be the order of the fluctuation, and then the limit is known to be the Tracy-Widom or the GUE eigenvalue. And similar results are known for geometrical LPP, and this was done by Johansson using connections to what are known as generalized permutations, and then you can take a geometric random variable, pass to the limit, and obtain similar things for exponential LPP. And here the shape theorem is slightly different, although still quadratic in nature, but you have universality in the fluctuation. So n to the 1/3 is still the governing factor, and then if you scale it by with some prefactor, you again reach the same scaling limit. Okay. And okay, so these are again fluctuation of this random variable, but now you can talk about transversal fluctuation of these paths. And this is where you actually need something more than this scaling limit. You need actually some tail estimates, because the real reason why you can sort of go from one to the other is the following. So suppose you know that the fluctuation is given by something, and if you have some tight control on the tail, then you can say that if there is a path which deviates too much, if a path goes like this and this, then there's a quadratic penalty because of the shape theorem, and then the fluctuation is not large enough to compensate for that. So, but if you have but this you can make rigorous only when you have a quantitative version of this thing. So a pre-limiting version of this scaling limit statement. Okay, and this is what is known as moderate deviation. So any questions so far about the sort of known results and these are sort of law of large number and just first order fluctuation. Okay. But in this talk we will sort of talk about very large deviations. So it's like so the typical fluctuation is of n to the 1/3, but now we will sort of talk about settings where the polymer weight sort of macroscopically deviates from what its typical value is. So in the Poissonian case, the typical value is 2n plus something which is n to the 1/3. Here we will talk about settings where the polymer weight is either 3n or n, so either way, but macroscopically deviating from the typical value. And more importantly, this is the geometric question that will govern this talk, which is on this rare large deviation event. If you condition on that, what is sort of the geometric property of the polymer? How do these exponents change? Okay, so typically we know the exponent is n to the 2/3. Now you can ask, like, if I tell you that the polymer is behaving atypically in length, what atypical behavior do you see in geometry? Okay. And so again, so there are of course two regimes. So you can talk about very high values and very low values. So this would be the upper tail large deviation. So I'll talk about it shortly. So the large deviation speed. So this will be of course exponentially small. The probabilities would be exponentially small. But in this regime, when it's larger than typical, it would be exponential in n. So the probability of this would be e power minus n. Whereas in the other direction, if you want the polymer to be shorter than typical, this would be exponential in minus n squared. Okay? So I'll describe why this is the reason. And so let's see. So the upper tail is n. So, okay, so we want one long path, right? So if I want the polymer to be long, I just need one long path. So I can take my favorite path, I can sort of make all the variables along this path super large, and that will give me one path which is pretty long, and so that would mean that the eventual polymer, which is the maximum among all paths, is also long. And of course, this is a sum of n variables, IID, and you can just use large deviation for that to get a lower bound, right? So this will give you a lower bound on the probability that an exponential in n lower bound on the probability that the polymer weight is more than typical. And so, but to prove the upper bound, you can use some standard concentration estimates like Talleyrand, or in the context of percolation, actually there was already a coarse graining or renormalization argument by Keston, which proves that it's also cannot be lower than exponential. So it has to be at least exponential. And of course, you can talk about now more precise things about existence of rate functions. And in this particular setting, you can sort of use some subadditive arguments. You can try to see that the probability of this event is also subadditive. And so that would imply that there is some limiting rate function. So log of this probability by n actually has a limit. Okay, so that was sort of the speed n story, and so then I said that the speed is n square for the other direction, and the real reason is because, okay, so if I want the maximum path to be smaller than typical, I have to that means that there is no long path in the system, right? That's the whole intuition, but it turns out that typically there will be many paths which are quite long, and so to reach the large deviation event, you actually have to make all of them short, okay? And so it turns out that you can actually find many disjoint paths completely lying in disjoint part of the space. So, okay, so we want Tn, which is the length of the polymer, to be smaller than mu minus delta n. Mu n is the typical value. So it turns out that typically there are many paths which have length at least mu minus delta by 2n. And these are all disjoint, in disjoint part of the space. So these are sort of discrete channels which are disjoint, and there is a path in each of them which are long. So you want to make all of them small. So of course, making each of them small has cost exponential in minus n, because it's again a large deviation of just sum of n variables. But now you want them to be true for all of these n independent paths. So you have an exponential in minus n raised to the n, and that gives you an exponential in minus n squared. Okay, so is sort of the reasoning clear? So there are many paths typically in the system that are very large. To attain the large deviation event, you want to force all of them to be short. There are all of these paths roughly lie in different parts of the space, so making one of them small does not affect the other. And so you have independent trials, each of them has exponential in minus n probability, so you take a product of them. And again, so a similar argument already appears in Keston's work on FPP, which is sort of a non-integrable version of this model that I've been talking about. Okay, again, so what is known about large deviation? So for Poissonian LPP, it was proved by Jean-Dominique Deuschel and Ofer, and also separately by Timo Sepulinian, that the probability of the polymer weight being bigger than 2 plus delta n, log of that divided by n converges to some rate function, which is convex, has all the nice properties. And again, for the lower tail, a similar result was proved, where you look at Tn smaller than 2 minus delta n. And the way this proves went was using connections to, again, this Young tableau combinatorics, like you have some exact algebraic object that you can count, and you want to understand how many of those objects correspond to the large deviation event. And if you can do that precisely, you can get results like that. Yeah, so this is exactly the number of permutations with a given length of the longest increasing subsequence. So you can, if you have a handle on those objects, then you can try to analyze them. And so I'll sort of quickly describe. Yeah, maybe I'll. Yeah, I don't know. So just to sort of exactly sort of say what the connection is. So there is something called the Young diagram, which I'll sort of shortly show, and then it turns out that the longest increasing subsequence of a permutation is exactly given by the top row of a Young diagram. And if you exactly know how many such diagrams are there, you can exactly compute the large deviation probability of this event. And using this, Kim had already proved the upper bound, and there was precise analysis of how many such diagrams exist by Logan and Shep. And what Ofer and Jean-Dominique did was use that to prove the lower bound. And this is, okay, I'll not go more into that, but this is what roughly a Young diagram looks like. And basically, this is the length of, so there is some measure associated to that. So you can sample a Young diagram with some measure, and it turns out that the first column is exactly the length of the maximal increasing subsequence of a permutation. So if you know how many such diagrams are there, where the first column has length 10, then you know exactly how many permutations are there, where the maximal increasing subsequence has length 10. For exponential LPP, it was proved by Johansson, similar large deviation results, where the constant is of course different, which is 4, and you look at Tn bigger than 4 plus delta times n, and he proved that log of that probability has the right convergence, and similarly for the lower tail. And here the connection that was being exploited was connections to random matrix theory and orthogonal polynomials. Okay, and again, so in the same paper, he proved similar results for geometrical LPP. Parallelly, Timo had already sort of proved the upper tail large deviation for this model using coupling with TSF, which I had described. Any questions? Okay. Okay, but now let's come to the question. So what is the geometric consequence of large deviation? So Deutschel and Zaytouni in 1999 studied what the path looks like conditioned on this large deviation event. For the upper tail large deviation in Poissonian, they show that even under this rare event, the path is still localized in the sense that the deviation is still submacroscopic. It's still little of n. And this is actually a consequence of the convexity of the upper tail rate function. Okay, so it's not too hard to predict that this would be still localized because typically the longest path is only n to the 2/3 away, right? The paths beyond that are typically shorter. Now if I want to make the longest path even longer, there's sort of no point in making the variables away from n to the 2/3 larger, right? Because that's sort of a suboptimal strategy. So any action that happens should happen at least within the strip of size n to the 2/3. So you can predict that the fluctuation exponent on this large deviation event is no more than 2/3. Okay, but now the question is whether one can pin down the right exponent. And so the question is, what is exponent? But in the paper, like nothing sort of could be said about what happened for the lower tail. All right, so that was the state of the art. So upper tail, the fluctuation is at most little of n. The question of the exponent remained open. While in the lower tail, it was not known whether it was localizing or delocalizing. Anything was not known. Nothing was known. Okay. And okay, so till now I was talking about general models, and but for the rest of the talk, I'll sort of focus on exponential. Okay, so transversal fluctuation. This is exactly the thing that we care about. And if I want to describe an exponent, so there is some complicated description, but okay, that's not very important. So you should try to understand. We should try to understand if there is an xi such that this is roughly like n to the xi. Okay, and so this is what we will call as the exponent. So if you look at the large deviation event that the polymer weight is bigger than 4 plus delta n, xi delta would be roughly the exponent which governs how far this deviates from the midpoint. Okay, so if it's n to the xi delta, we'll call that as exponent. And so the main result is that this exponent exists for any delta and is equal to half. Okay, so we know for a random path, if you just took a random walk from 0 to n, the fluctuation would be n to the half. And it turns out that if you condition the polymer, which typically has fluctuation n to the 2/3, if you condition that to be longer than typical, the exponent becomes 1/2. Any questions about the result? How much time do I have? 20 minutes. Okay, and so the upper bound, we currently have, although I'll sort of say more about that, so you can really sort of improve on that. But for the moment, what I'll discuss in this talk is the upper bound where we show that under the large deviation event, so U delta would be my large deviation event that the length of the polymer is bigger than 4 plus delta n. So I condition on that, and then this upper bound result says for any epsilon, the probability that the maximum transversal fluctuation is bigger than n to the half plus epsilon converges to 0 as n goes to infinity. Although you can really improve on that, so I'll sort of mention this later. Whereas the lower bound, the result that I'll talk about is, so now this is sort of a slightly different statement. We say that, again conditioning on the same event, the probability that dn, the fluctuation, is smaller than h times n to the 1/2, h you can think of as a constant, goes to 0 as h goes to 0. So if h is epsilon, then probability that dn is smaller than epsilon times n to the 1/2, condition on this event would be something which goes to 0 as epsilon goes to 0. Okay? So here epsilon appears in the exponent, here epsilon appears as a multiplicative factor. Yeah? No, this is again, so throughout the rest of the talk I'll focus on, throughout the rest of the talk I'll focus on exponential. Although, so we have some idea of how to make this work for other integrable models, but I don't know how to do this for any non-integrable model. Yeah, and so, okay, so if there is time, I'll talk about the lower tail, but for the moment, let's focus on the upper tail and try to prove this n to the 1/2 fluctuation. And so this is where I'll sort of exploit connections to random matrices and eigenvalue rigidity. I'm not sure if I'll get there, but like, we have some results for the lower tail as well. Okay, so what is a key integrable input? And so this is where the V-shot ensemble comes into the picture. So let's say X M cross N is an M cross N matrix whose entries are standard complex Gaussian entries, okay? So every entry has variance 1. And so you look at the V-shot matrix, which is X star X, and look at the eigenvalues lambda 1 through lambda n, ordered. And turns out that this distributional identity is true. So if you look at the polymer weight from 1, 1 to m comma n, that as a random variable is equal in distribution to lambda 1. Okay, so you take a complex V-shot matrix, look at the largest eigenvalue, and that is equal in distribution to this passage time that we were talking about. Okay, and this already appears in the paper of Johansson, and this is sort of one of the key things that he uses. Yeah, so this is the theorem that appears in Johansson's paper. Lambda 1 is in distribution same as T1 1 comma m comma n. So again, recall, so Johansson already had proved this large deviation existence of this rate function, and similar results have been proved by Majumdar, who's here, and co-authors relying on Coulomb-Gus methods. And the key improvement of this that we need to deduce what we want to deduce is this refinement. So probability lambda 1 bigger than 4 plus delta roughly looks like e power minus n I delta, which is this large deviation statement. But to make this deduction, you need these correction terms, and it turns out that the correction is minus log n plus order 1. Okay, so it's e power minus, so if you exponentiate everything, oops. Yeah, so if you, yeah, thanks. So if you exponentiate everything, then the prefactor is just a polynomial. It's like 1 over n. That's important. So the constant before log n is 1, and then the other correction is just a constant. Okay? Okay, so there is some complicated expression for the rate function. Let's not worry about that. Okay, so let's skip that. So I has some nice properties. It's okay, so how does one try to prove this? So again, we will use the joint eigenvalue density of the V-shot matrix, right? So that's sort of the natural thing to do. And okay, so it's not terrible. So again, so this is the Vandermonde term, which I'll talk about. There is some lambda to the m minus n term, and these are the exponential terms. And this is a partition function that makes it into a probability measure. So V lambda is the sort of Vandermonde term that appears in all over the place in such contexts. So product of lambda I minus lambda j. And the partition function actually turns out to have a not too terrible expression. So it's a Selberg integral, but you can actually do that, and then it just comes out as some gamma functions. You can sort of use gamma functions, and this is what it comes down to. Okay. Okay. So given this, one thing that would be useful is to sort of have an understanding of the ratio of the partition function. So you have a system of size m comma n, and now you have a system of size m minus 1 comma n minus 1. So because of this sort of explicit expression, you can actually work out how the ratio of the partition functions behave. Okay, so there is some expression. That's going to be important for us. Okay, so now we will sort of try to sketch how using all this inputs, you can try to sort of refine this large deviation result. Okay, so among the Vandermonde, so the whole game, which has been done many times before, is to look at the system of size n. You have n eigenvalues. You want to understand the large deviation for lambda 1, which is the largest one. So you can sort of look at this density, and you can decompose that into lambda 1, the stuff that depends on lambda 1, and the remaining stuff that is sort of, you can think of that as a smaller dimensional system. So it sort of roughly looks like a joint eigenvalue density for a matrix of size n minus 1. Okay, so you have start from an eigenvalue density where there are n particles. You want to understand the largest one. Ignore that, ignore everything that depends on that. Everything else looks like an eigenvalue density for a smaller system. So the part of the Vandermonde term that depends on lambda 1 is exactly product of lambda 1 minus lambda j, where j not equal to 1, right? So these are exactly the factors that have lambda 1 in them. So okay, so we want to compute this. Lambda 1 bigger than 4 plus delta is this density, the joint density of n eigenvalues on this region lambda 1 bigger than 4 plus delta, of course, triviality. But now you want to sort of make some manipulation, so you want to so remember the density has a z nn downstairs, right? That's what makes it a probability measure. But you can sort of, if you want to reduce it to an n minus 1 dimensional system, you want to multiply and divide by this n minus 1 dimensional partition function. So Zn minus 1 and n minus 1 comes here, and you divide by that, and then you reduce everything to a density of size n minus 1, okay? And this is the remaining term. So these are the stuff that depends on lambda 1. So this is the term that from the van der Monde term comes out, which is this. And then you have some exponential in minus n lambda 1 that was taken out. And then you also actually, to make it into exactly the density, you also factor out some extra lambda i's where I is bigger than 1, okay? So you can do some manipulation. Okay, not so important. So rearranging the term in the exponential, so here is an exponential. So there is a term here, and I want to sort of look at it as exponential of something. So the van der Monde term becomes a log, right? So it's a sum of logs, and then you have some minus summation lambda I from I equal to 2 to n. And now you're integrating this with respect to the density of n minus 1 dimensional eigenvalues, right? That's what it sort of, the whole thing in the previous slide did. And the whole goal is that this thing should be concentrated. Because the n minus 1 dimensional eigenvalues are rigid, they are in some precise locations, so this thing should be super concentrated, which should then give you the refinement of this large deviation probability that you want. So this is, so we are integrating this with respect to the empirical spectral measure, and now you want to use rigidity to say that this is in fact very close to the integral with respect to the Marchenko-Pasteur law, which is the scaling limit of this spectral distribution, right? So for this Wishart that we're talking about, the scaling limit of the empirical spectral measure would be the Marchenko-Pasteur law. So that we have talked about in this week before. And so this manipulation combined with the fact that this sum, which is the integral with respect to the spectral measure, is concentrated, tells us that this thing is approximately, with very high precision actually, is like this. So it's an n minus 1 dimensional system, so you have an n minus 1. So there's a 2 here, and then you have the sum becomes an integral, so log of lambda 1 minus x with respect to the Marchenko-Pasteur. So MP is Marchenko-Pasteur. This one is minus x times, so it's just expectation of a Marchenko-Pasteur, and then you have some correction which is order 1. Okay? So I just did some sort of manipulation to reduce an n system to an n minus 1 system, wrote things the right way so that the thing on the top was an integral with respect to a spectral measure, and then use rigidity to say that that's close to what it should be in limit. And so, okay, so there is some technicality. So this order 1, you have to have some uniformity because you're then integrating with respect to lambda 1. So you need some uniformity in order 1, this order 1 correction. And that is not hard to achieve on a compact interval. So the point is, if you now just look at the integral of lambda 1, so we wanted it to be bigger than 4 plus delta, but let's also say that you want it to be less than L. Because everything outside L is so unlikely that it will never happen, so you can ignore them. But this is a compact interval, and so that order 1 thing you should be able to control that uniformly. So manipulating things, so what this turns out to be true is this is exactly exponential of this rate function. I is a rate function with some correction, and then you integrate over this interval, okay? Right, so you manipulate, and then you want to integrate over lambda 1. So till now there is no log factor, right? So I want e power minus n I delta minus log n plus some correction. So till now I just have this rate function, okay? But this integral is what will give you this log n. So you have this lambda 1, now you can you want to integrate this thing over an interval of compact size. Now you can discretize, approximate the integral by your Riemann sum. So you will have something here, the Riemann sum is over intervals of size 1 over n, so you have this 1 over n coming up. And it turns out that this thing, the exponential, has a geometric decay, so that's summable. So that will actually not affect anything, so that will give you another order 1 correction. And so this is the 1 over n in the Riemann sum is exactly what gives you this log n, okay? So you have this discretization, this gives you a prefactor of 1 over n. This thing is geometrically decaying, so you can think of that being replaced by I equal to 0 case, which is exactly e power minus n I delta. The 1 over n is a log n, and then everything else is sort of absorbed in this order 1 term. Oops, yes, I'm really doing bad on time. So, okay, so let's see. Yeah, so the lower bound is not, so the lower bound again follows by the same logic. Okay, so what is exactly used to make this thing rigorous? One is this concentration of Lipschitz functionals for smooth linear statistics using log-sub inequalities. So this is the result by Alice Guin and Ofer. So where you look at the smooth linear statistic of this form, so lambda is again the eigenvalues, you look at the average of them, It turns out that they're super concentrated with Gaussian concentration, but near the expectation. So this is the random thing, which is a smooth linear statistic, and they have Gaussian concentration around its expectation. Remember, we want to compare everything with the limiting marching capacitor. So then the remaining step is to show that this itself is close to the marching capacitor. And so then you can use various results. So when we first did it, we sort of saw this result by Gotze and Tikhomarov, which shows that the Kolmogorov-Smirnov statistic between the marching capacitor and the expected spectral measure is like 1/n. If you use that, then you can use some integration by parts to, right? So if you have some bound on the Kolmogorov-Smirnov statistic, you can bound how expectations differ by just integration by parts. But as Ofer pointed out, that this was really sort of not the right thing to use. So there are several other results by Bai and Silverstein, Alice, and Johansson, which actually does the job. So this was, there are other results which you can also use. Okay, and so because I do not have too much time, I'll just try to show how to prove the lower bound using this refined large deviation principle. Okay, so you want to prove the fact that the polymer moves by at least √n, right? That's a lower bound statement. So one way to do that would be to show that the probability that the polymer passes through any given point is at most 1/√n. If you show that the condition on this upper tail event, the probability that the polymer passes through a given point is at most 1/√n, that would mean that the polymer at least should deviate by √n. Okay, so what is the probability that the polymer passes through this midpoint? Okay, so it's again the sum of two independent things. So you look at the polymer from this point to the midpoint, and then you add the polymer from the midpoint to n. And so let's call that midpoint to be V star. Then you want to really understand the probability of this. So T0 V star was the first part. This was the red part, the blue part. And T prime V star n was the red part. So you have these two parts. You want to look at the probability that the sum of these two things is bigger than 4 plus delta n, condition on the event that the polymer itself is bigger than 4 plus delta n. And so this is the statement that I just made. If you can show that this is 1/√n, you should have a lower bound. And so this is nothing but convolution of two IID copies, right? So T0 V star and T V star n are the same in distribution. And for each of them, we have a precise large deviation principle. So you're basically trying to compute so this thing you should be able to bound this using convolution of those two, right? And so this is exactly what we do. So this is exactly the conditional probability. So because you're looking at a convolution, so the first part can be 4 plus delta 1n, the second part can be 4 plus delta 2n, and you want to look at sum over all possible delta 1 and delta 2 so that the sum is at least delta, right? That's exactly what a convolution is. So let's try to fix some delta 1 and delta 2. Let's say delta 1 is delta plus I by n, and delta 2 is delta minus I by n. And so you want to bound this. Okay, you do some algebra, and you use the precise form of the large deviation that we have. So you have a minus log n at the bottom, you have minus 2 log n at the top because there are two factors, and you have I delta 1 plus I delta 2 at the top, and you have an I delta at the bottom, right? That's exactly the ratio. But delta 1 plus delta 2 is delta, so you can use some Taylor expansion. So if you do a Taylor expansion, the linear term will cancel out, and you will end up with a quadratic term. So it's some double derivative that you don't care about. You will have an e power minus I square by n term. So that's like a discrete Gaussian. So forget the 1/n for now. But now you have to sum over all possible delta 1 and delta 2, right? So summing over all I tells us that this is like √n. So remember, discrete Gaussian is like e power minus x squared by n by √n. You have a √n missing here. So if you add all of them up, you will get a √n. And you have a 1/n outside, so the whole thing will be like 1/√n. Is this computation roughly clear? So it's nothing very deep. So once you have this refined large deviation result for each of these factors, you can try to do a convolution. You have so something appears at the top that you know precisely, something appears at the bottom that you also have good control over. It turns out that you do some Taylor expansion, you get some discrete Gaussian type object, you sum them up, you get a √n contribution, but then there is an additional 1/n outside, which gives you 1/√n. Okay, and so, but the point is this only proves that passing through the midpoint is like 1/√n. But you want to show that that bound holds for every point. Only then can you sort of deduce a lower bound. And so here something sort of slightly general works, which is not very specific to this model, which is that this is monotone. This probability of the polymer weight passing through the, the polymer passing through the origin, the length of that stochastically dominates the polymer passing through any other point. And so one way to deduce that is by using some general results about stochastic comparisons for determinantal processes. So I'll sort of, because I'm sort of almost running out of time, I'll sort of stop with this, okay? So we thank Manju for pointing this out. So this is exactly the general thing that will tell us that the polymer weights are stochastically ordered as random variables. So let's say Y is an m plus 1 cross n minus 1 Bichat matrix. So I want to compare the largest eigenvalue of this matrix with the largest eigenvalue of the Bichat matrix of size mn. And I want to say that the latter one is bigger than the other in stochastic sense, okay? And so this is the statement which says that there exists a coupling such that the eigenvalues lambda 1 through lambda n minus 1 of this new matrix is a subset of the n eigenvalues of the Bichat matrix that I started with. And so in particular, the largest eigenvalue has the right ordering. And the largest eigenvalue is exactly the passage time. Okay, so I want to say that the passage times are stochastically ordered. I use the eigenvalue correspondence. I have to show that the eigenvalues are stochastically ordered. And the eigenvalues form a determinantal process. And if I can show some sort of a stochastic comparison about the processes themselves, I can make the deduction. And so the real reason why this is true is because this already appears in some abstract sense in a paper of Russ-Lance, that you can find a coupling where you can sort of make this ordering statement work if the kernels of these determinantal processes are ordered. And now it's not very hard to check that if you take a Bichat matrix of size m, so let's forget the m. You take a Bichat matrix of size n, n, and take a Bichat matrix of size n plus 1, n minus 1, then you can try to figure out, and it's not very hard to see, that the kernels corresponding to the point processes that are the eigenvalues, they are ordered in this positive definite sense. And once you have that and you use this abstract result, the lambda 1s are ordered, which means the passage times are ordered. And so the previous argument that showed this 1 over root n bond for the midpoint works for any other polymer. So this says that no matter where you are on the antidiagonal, the probability that the polymer condition on this upper tail event passes through that is at most 1 over root n. So this gives you a lower bound. For the upper bound, it's more complicated because this sort of monotonicity is not useful. So you have to have some real understanding of large deviation for non-square Bichat matrices. So because the midpoint really sort of depends on n cross n matrices as you go away from the diagonal, the Bichat matrix that comes into play is m cross n. And so you have to sort of use rigidity results for such non-square matrices. And luckily they're available. So we use that and so you can sort of do some precise computation, 2 minutes, 1 minute, 1.5 minutes, okay. Yeah, so anyhow, so let's skip all this. Yeah, so for a non-square matrix, you again have a precise large deviation event, but the rate function now depends on the aspect ratio. So if you look at a rectangular Bichat matrix, the rate function will depend on how rectangular it is. Okay, so let's not worry about that. But this is the key comparison result. So look at a Bichat matrix of size m1, n1, where m1 and n1 are perturbations of n. So this lemma tells us how the rate function for this non-square matrix compares with the square matrix. It turns out that the comparison has some e power minus c square over n term, where c is the deviation, so how non-square it is. And this quadratic exponential of this quadratic is really the reason why root n is the right fluctuation. This is what gives you the upper bound. Okay, so the lower bound uses monotonicity. For the upper bound, you need more quantitative estimates, and this is it. Okay, so 30 seconds more. So let's forget that. Okay, so this is our proof. Let's skip that. So just one comment. So for the lower tail, so for the upper tail, we proved that the fluctuation exponent is n to the 1/2, right? It's 1/2. It turns out for lower tail, which has speed exponential in minus n square, there is complete delocalization. The path condition on this lower tail event is actually macroscopically away from the diagonal. Okay? So this is joint work with, okay, so I forgot. So whatever I mentioned was joint work with Riddhipratim. And this one, the lower tail result was done last year, also jointly with Alan Sly. Yeah, so this is the result. The precise statement is not super important. So I'm done. So I'll just mention one open question. Blah, 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 blah. Yeah, okay, so yeah, let's end with one question. Can one prove that the scaling limit of the polymer condition on this upper tail event is a Brownian bridge? Okay, so we know that this exponent matches that of a random walk path. Can you prove a full scaling limit of this polymer? And so for the typical case, so the question of proving a scaling limit for the polymer when there's no large deviation is just typical. It was not known even like last month. I don't know, like there was some progress last month by Balin Virag and co-authors where they they make some major breakthroughs, and it might happen that it could be a consequence of that, but I'm not sure. But certainly for the large deviation case, this is an open question, and I'll stop here.